Hello teachers! In this section 3-3 we want to talk about subtraction of whole numbers. We're going to spend some time on the meaning of subtraction by studying various models. We're talking about the inverse relationship between addition and subtraction. We'll definitely go through subtraction algorithms just like we went through addition algorithms, including the standard algorithm and how to use them. We're going to do subtraction with number bases other than 10, so base 8, base 12. Mental subtraction computational skills, which are very helpful and good estimation techniques. Subtraction of whole numbers can be modeled in several different ways. We'll talk about the takeaway model, which views subtraction as a second set of objects being taken away from the original set. We'll show that model. The number line model, where subtraction is represented by moving left on the number line, giving a number of units. And we'll also talk about the missing add-in model, which is an algebraic way of thinking where students compute a difference between determining the value of an unknown add-in. So the subtraction of whole numbers takeaway model. So I'm sure you recall this from elementary school. And so if we have 8 blocks, and think about this like a Venn diagram, we have 8 blocks all together. We want to take away 3. That model's 8 minus 3. You see we have 5 blocks left. The visual of that is great. And that's called the takeaway model. Now we can also do the number line model. Very important to visualize this on a number line. Notice we start with 5. That's the lower value designated on the number line, and then we subtract 3. So we go from 5 and go backwards 3. Again, taking away is moving left on the number line. If you recall, addition is moving right on the number line. And then your result is what you have remaining. Of course, 5 subtract 3 gives us 2 on the number line. And then you have the missing add-in model. So 8 subtract 3. And what you do is imagine what you would add to 3 to get 8 back. Notice they point out this can be thought of as the number of blocks that must be added to 3 in order to get 8 as a result. The number 8 minus 3 is missing the add-in in the equation. So 3 plus what number gives you 8? And when you visualize this in a picture format using blocks, you have 3 already. What do we need to add to that 3 to get to 8? Well, we would be missing 5 blocks. Or if you look at that on a number line, again, you have 3. What do I need to add to 3 to get to 8 over here on the number line? So the missing add-in model applies to both the number line and the blocks. Now we have a definition of subtraction of whole numbers. This isn't the only definition. I'll show you a different way to think about this momentarily. For any whole numbers A and B such that A is greater than or equal to B, that's very important. A minus B is a unique whole number C such that B plus C is equal to A. That is the definition of subtraction. Why do you imagine A has to be bigger than B? Keep that thought. Now what we know is A is called the minuend and B is called the subtrahend. Remember, when you're adding, the values added are called the add-ins. So we have a minuend and the subtrahend. Now I do want to point out down here at the bottom, the highlighted area, there is another definition for subtraction where you don't have to compare the two numbers. It's for any whole number A and B, A minus B is the unique whole number C if it exists such that B plus C is equal to A. And again, it points out that A is greater than or equal to B has been deleted, and if exists, works instead. Now again, back to why does A have to be bigger than B? Well, if you subtract and A were less than B, notice you would not get a whole number as an answer. And so that's why A has to be larger than B. Now when you're teaching elementary school, you'll spend a lot of time talking about fact families likely. A fact family is a group of related facts using the same numbers. So the following is an addition, subtraction, fact triangle, emphasizing fact families. It has two add-ins and a sum. So notice what's going on here. If you look at 7 plus 5 is equal to 12. Okay, so in our fact family, we have 7 plus 5 equals to 12. You could also write that using the commutative property of addition is 5 plus 7 equals to 12, part of the fact family. But also, you can subtract. We know that 12 minus 5 is equal to 7, or we can say 12 minus 7 is equal to 5. And that is your entire 4-entry fact family. So let's try that with one of these examples below. We don't have to do both of them, but if we take a look at 7, 8, and 15, if we want to draw the fact family triangle, now what would go at the top? That would be the larger number 15. Why? Because 7 and 8 add to be 15, and you're considering the plus minus, so you could say 15 subtract 7 equals 8, or 15 subtract 8 equals 7. And then if we made our fact family list over here for 7, 8, and 15, we know 7 plus 8 is equal to 15. We know 8 plus 7 is also equal to 15 by the commutative property of addition. We know that 15 minus 7 is equal to 8, and 15 minus 8 is equal to 7. So that's the 4-entry fact family for 7, 8, and 15. I know if you needed, you could do this for 4, 7, and 11, and you'll find yourself doing this in the homework as well. Now, another way to model subtraction is with the comparison model. If we wanted to discuss 8 subtract 3, then we could start with Juan's 8 blocks and Susan's 3 blocks, because we know that Juan has 8 blocks and Susan has 3 blocks. How many more blocks? Then if we compare Susan's 3 blocks, pair up with 3 of Juan's 8 blocks, and then the difference would be clear to see over here with 5 blocks. So anytime you're trying to calculate the difference between two values, the comparison model works really well. Let's spend a few minutes talking about properties of subtraction. Does subtraction have a commutative property, an associative property, and an identity property like addition has? We know that in addition you have a commutative property of addition. I encourage you to think about commutative as like you commute to work. You're traveling back and forth to work. Well, you commute in addition, you're moving your values around. 2 plus 3 equals 5. 3 plus 2 equals 5. Is there a commutative property of subtraction? And to discover this, you might just want to come up with an example. For instance, we know that 8 subtract 3 is equal to 5. Is it also true that 3 subtract 8? Notice that's commuting, moving the values around. 3 subtract 8. Does that also equal 5? And of course your first thought is no, and some of you even might have thought, well, it's equal to negative 5. But remember, we're talking about whole numbers here. As a matter of fact, subtraction is not even defined where the minuend is smaller than the subtrahend, because we don't get a real number. Turns out subtraction is not closed in the whole numbers. It's not a closed system. So we can do 8 minus 3 equals 5, but it is not true that 3 minus 8 equals 5. So there is no commutative property of subtraction. What about an associative property? So once again, addition has an associative property. If you'll recall, 2 plus 3 plus 5 is equivalent to 2 plus 3 plus 5. That's the associative property of addition. You're associating different values together. What about for subtraction? Is something like that true? So let's make up an example. So 5 minus 3 minus 5. I did that wrong. Let's start bigger over here. I didn't think that one through. let's do 10 minus, and let's switch this around also, right? You see where the example went wrong. I'm not allowed to subtract those values. 10 minus 5 minus 3, is that equivalent to, we have to regroup. So 10 minus 5 minus 3. Are they the same thing? Well, 10 minus 5 minus 3 is the same as 10 minus 2, because 5 minus 3 is 2. We're required to group those together and subtract first. 10 minus 2 is 8. Over here on the right, 10 minus 5 is 5. Subtract 3. 5 minus 3 is 2. And these are definitely not equal. So is there an associative property of subtraction? There is not. Now let's talk about an identity property. Remember with addition, the identity property is we take, for instance, 5 plus 0 equals 5, which also equals to 0 plus 5. Now the question is, can we extend that to subtraction? Now at first thought, it might seem like, sure, we can do that. And I'm going to erase a little bit of our work here for the associative property just to get the space back. But if we take 5 minus 0, it looks like we have an identity property because 5 minus 0 equals 5. But the identity property says you have to be able to do that the other way also. So 0 minus 5 is not equal to 5. So it turns out we do not have an identity property for subtraction. Even though 5 minus 0 equals 5, we don't have that commutative situation where we could also say 0 minus 5 is equal to 5. So no commutative, no associative, no identity property for subtraction. It can be shown that if A is less than B, then A minus B is not meaningful in the set of whole numbers. Therefore, subtraction is not closed over the set of whole numbers. We mentioned that just a few minutes ago. We know that 8 minus 3 is equal to 5. But in reverse, when A is less than B, for instance, 3 minus 8, that is not a whole number. Now you might be thinking, is it that negative 5? It is. And negative 5 is an integer, a negative integer, but not a whole number. So subtraction is not closed on the set of whole numbers. You have to have A greater than or equal to B to be able to perform subtraction within the whole number system. Now early on we want to get our students used to thinking algebraically, even if we don't use variables to denote missing values. But if you have 9 plus 5 equals something here, and 12 minus something equals 4, can be true or false depending on the missing value. So for example, if your sunshine here is equal to 10, then 9 plus 5 equals 10 is a false statement. If you have your diamond is equal to 8, then 12 minus substitute 8 equals 4 is a true statement. So if the value that is used makes the equation true, it is called a solution of the equation. And we talk about this a great deal in algebra, but way before students ever study algebra, you want to introduce algebraic thinking in your early grades. All right, let's spend some time talking about the concrete model here. So we're using our base 10 blocks, correct? We want to represent 243 minus 61 using our base 10 blocks. So you begin with 243. Okay, so if we've got 243, we've got two flats. If you'll notice, we have two flats in the picture. Each flat is worth 100, so 100 plus another 100, that's 200. We've got four longs here to represent 40, and then 3 unit blocks to represent, of course, 3. We want to remove 61. Now, as you can imagine, you could actually do this without pulling things apart, but I want you to get in the habit of splitting up what you need. So we could subtract the 1. We could remove this 1 right here, right? But we don't have 6 longs to remove. We have 4 longs. So what we want to do is split up this flat into 10 longs so we could subtract the 60. So what are we going to do? We're going to trade, right? We're going to trade in. Now, often in the past, this is the way that I was educated, and I still use these words, we borrow. But really what we're doing, a better way to think about it is you're trading. You're trading in 1 flat for 10 longs. Notice that's what happened. We traded in 1 flat. If you count them over here, you got 10 longs. And now we can take away our 61, which is represented as 6 longs. Now, count over here, 1, 2, 3, 4, 5, 6. Those are X'd out, plus the 1 unit to represent 61. And of course, your result is your final answer. And your result is right here. So you have 100, because remember a flat is 100. We have 1, 2, 3, 4, 5, 6, 7, 8 longs, which represents 80, and 2 units. So 182. Now another algorithm that I find quite useful, and especially when I'm working with not base 10, is the equal additions algorithm. Now notice what we're trying to do. We're doing 255 subtract 163 in the left-hand column here. Now the next step is I'm trying to convert 163 to the next 10 higher, okay? So I'm going to add 7. So again, I see this 3. I'm going to add 7 to 163 to make it 170. But to do that, I have to equally add 7 to our minuend. So I add 7 to our subtrahend, and I add 7 to our minuend. And this is an equivalent subtraction problem. All right, so when I do that, that's going to give me subtracting 170 from 262. I could even do it again. I can go to the next 100 level. So what do I need to add to 70 to move up to the next 100? I'm going to add 30. Again, if I add 30 to the subtrahend, I have to add it to the minuend. Okay, 262 plus 30 is 292 minus 200, and then you have an easier subtraction problem. So instead of trading in, which again we've called borrowing in the past, instead of trading in, I'm just going to add the same values to my minuend and subtrahend and get an equivalent problem, which is a little easier to do the subtraction. And we also have the counting up algorithm. Now, if you've ever worked a cash register, especially an old cash register, this is a method that you would use to count back money. I'm going to read this. This algorithm can be best described as the making change method. It is the way that cashiers and tellers give change for purchases. Today, with calculators and computerized cash registers, that's become sort of a lost art. However, it is a way to do subtraction in your head. It uses the idea of the missing add-in model for subtraction. Students are encouraged to count up to nice numbers, which are multiples of 10, 100, 1,000, and on. So I'm going to show you an example where you do this. So if we are going to subtract 100 minus 31 using the counting up algorithm, we're going to start with 31, your subtrahend, and count up to the next 10 value. So I'm going to add 9 to that. And then I'm going to count up again to 100. I'm trying to get to this value. So I start with the 31 and I count up to get to 100. So again, I add 9. And then up to get to 100, I add 60, and that means my result is 69. Here's another way to think about this, and this is really in action. Noah owed $11 for his groceries. He used a $50 bill to pay. So if you think about that, you're calculating $50 minus $11. But what the cashier did is started with 11 and started counting up to the next whole number. So notice here's the count. 11, and then 12, which added $1, 13 added another $1, 14 added another $1, 15 added another $1. But now we can move to a 5 denomination. So 5 takes us to 20, and then a 10 takes us to 30, and then another 20 takes us to 50. And then you add the money back here that Noah received. And once again, can't get the pen to work. $1, 2, 3, 4, 9, 19, $39. You should practice that if you've never done that. And there it is spelled out for us. We know that 50 subtract 11 is 39, but we didn't actually do the subtraction. Again, we counted up and he counted 12, 13, 14, 15, 20, 30, 50. And then there we go. Then we have this idea of the trades first algorithm. Notice it points out it's very similar to the standard algorithm. And you could picture the standard algorithm when we're working with blocks. And we trade either a flat or a long. Okay, again, we call that borrowing in the past. We're going to call it trading now. This algorithm is very similar to the standard algorithm, except that all the regrouping is done before any of the subtraction is carried out. Using base 10 blocks may help with students' understanding of how to subtract. So let's just take a look at an example. We want to subtract 37 from 122, so we need 122 blocks. Notice I have this very tiny for you, but let's look in our first row here. So we have a flat, which represents 100. We have two longs, which represents 20. And then our ones over here, 2 units to represent the 2. Now, if we want to subtract 37, we know immediately we can't subtract 7 units from only 2 units. So we're going to trade in. We're going to trade in one of our longs for the 10 units over here. Okay. But now if you look at our 10s, we can't subtract 30 or 3 longs from 1 long. So we're going to trade in again. We're going to take one of these flats, and we only have one, and turn it into 10 longs. So if you'll notice here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Because we already had a long, we traded that entire flat for 10 more longs, and now we have 11 longs. And we can simply cut out the 7. I'm going to do that. So we're going to get rid of 7 of our units. So there's 1, 2, 3, 4. Getting frustrated with the pen. So 4, and then 5, 6, 7. Okay. And then we're going to get rid of 3 of our longs. There we go. Notice that we still have remaining, I'm going to count, 1, 2, 3, 4, 5, 6, 7, 8. They're arranged down here as 8. And then 1, 2, 3, 4, 5 units. And 1, 2, 3, 4, 5 units. So our final answer is down here in the last row. Does that make sense? But notice we traded everything first before we did any of the subtraction, although we had to think about what we had to subtract to do the trade. And you can also do this in table form. So we started with 100, 2 10s, and 2 1s to represent 122. We're trying to subtract 37. I can't remove 7 from 2, so I'm going to trade in one of those 10s and add that to the 2 1s, which gave me 12. I can subtract 7 from that now. And here we also had to borrow one of our 100s and our only 100 to add 10 more 10s, which gave us 12 10s, and we're going to subtract 3 from that. Actually 11, because we had to borrow one over here to get 8. Okay, and I think visually with the blocks is a lot more clear than probably this table form, but I wanted to show you the table. Now, what do we have to subtract using bases other than 10? Can we pull this off? When you have to trade in, you know, it might be a little bit different. We're not borrowing tens and hundreds or trading in tens and hundreds. So let's see what we could do with this. One way to get started is really to complete a table for addition, and this is for base 5. So let's take some time to do this. So when you complete this table, notice you're adding 0 plus 0. 0 plus 0 is 0. 0 plus 1 is 1, even base 5. 0 plus 2 is 2. 0 plus 3 is 3. And 0 plus 4 is 4. Why doesn't it go any higher? Because remember, we're dealing with base 5. Okay, our digits only go between 0 and 4, and that's it. Let's keep going. 1 plus 0 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 4 is 5. But we don't have a 5, right? The 5 carries over to the next place. So we have 1 5 and 0 1s. Remember, that's not read as 10. That is not the numeral 10. It doesn't represent the number 10. That is 1 5 and 0 1s. All right? So 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5, which is written as 1 5 and 0 1s. What about 2 plus 4? Well, 2 plus 4 is 1 5 with 1 1. 3 plus 0 is 3. 3 plus 1 is 4. Here we go again. 3 plus 2 is 5, which is 1 5 and 0 1s. 3 plus 3 is 6, which is 1 5 and 1 1. 3 plus 4, and again, it's not really 6. It's the number 6 we have visualized in our head, which is 1 5 and 1 1. Just like 3 plus 4 is the number 7 we have in our head, which includes 1 5 and 2 1s. 4 plus 0 is 4. 4 plus 1 is 1 5 and 0 1s. 4 plus 2 is 1 5 and 1 1. 4 plus 3 is 1 5 and 2 1s, and 4 plus 4 is 1 5 and 3 1s. So there is our table completed. I have it typed up for you. There you go. Now, what are we going to do with that table? Well, let's see if we can do the subtraction problem. So notice what's happening here. We are not trading in right off the bat. We're taking our subtrahend, which is 43, and we don't read it 43, right? It's really 4 3, just like we're taking 4 3 2 base 5 and subtracting 4 3 base 5. Now we've decided to add 2 to the subtrahend. Why are we doing that? Because that 3 plus that 2 is a 5, but we don't write 5s in base 5. It goes over to the next, right? We're trading in, okay? And if you recall, that's called the equal additions algorithm. So again, I'm adding 2 to make that 3 plus 2 is a 5. So that's going to carry over to that 4, and it's going to make 5 5s and 0 1s. But I'm also going to add those 2 1s to the 2 1s right here. You ready for that? Again, this is called the equal additions algorithm. So the 43 here, the 2 plus 3 gave me 5, which makes that 5 5s, but we don't have that either, right? Because we don't have the unit 5. So that gave me 1 0 0 base 5. When I added 2 to 43, make sure you see that. And then when I added the 2 units to the 2 units, because that's not 5 or larger, it doesn't trade over. We don't have to regroup. That's what that's called. So borrowing we call trading, and the old word carrying is regrouping, is what we're doing here. Now notice this. We can take our 4 units and subtract 0 units and get 4 units. We can take our get my pens to work. So again, 4 units minus 0 units gives me 4 units. I can take my 3 5s minus my 0 5s, and that gives me my 3 5s. And I can take my 4 5 squares minus my 1 5 squares, and that's going to give me my 3 5 squares. So this subtraction is 334 base 5. That takes some practice for sure. So make sure you see that. Watch it again if you need it. If you need me to do another one of those someday, just let me know and I'll make another video. Okay, now, what if we tried a different problem, but looking at blocks instead? So these are base 5 blocks instead of base 10. My problem I'm highlighting over here, it's really tiny. We're looking at 32 5 minus 1 4 5. Again, I caution you not to say 32 5 minus 14 5 because that's not what it is. It's 3 5s and 2 1s minus 1 5 and 4 1s. So let's set it up. So just like we said, that's 3 5s and 2 1s. So notice we've got 3 5s and 2 1s drawn. We're subtracting out, so we're trying to get rid of 1 5, that's this, and 4 1s. And there we go. Now to do that, we had to take away, or what do we call that? Trade in one of those longs, which again, it's a base 5 long, and they're just put them on their side. Notice 1, 2, 3, 4, 5, and then the 2 we already had are right here. And then we subtract it out. Notice what we're left with. We're left with one of our longs here, so that's 1, and then 3 units left total that we didn't take away. So 1 3 base 5. And it shows it here worked out as well. But I think it's easier to think about in picture form, far easier. And then one more thing we want to talk about before we wrap this video up. Again, I'm over my time, but this will just be a part 1, no part 2 for subtraction, is mental computation. So you want to be able to do mental computation. Of course, you want your students to be able to easily do mental computation. And there's a few different techniques for this. One of them that's great is breaking up and bridging. Notice what we're doing here. We're trying to subtract 74 minus 26. If you start with your 74 and then just subtract 20. Don't deal with the 6 units yet. Just subtract 20 out. That's easy to do in your head. That gives you 54. And then subtract the 6, which is going to give you the final result of 48. I think that's worth practicing in your head. So again, if you're dealing with 2-digit numbers, okay, then take the minuend and subtract how many 10s you have, and then subtract the 1s from that result. Now what about trading off? We used trading off when we worked with, and we also called it, let me back up real quick for you right here, it's the equal additions algorithm. You could also call that trading off, where we add the same value to the minuend and the subtrahend. And so to make that a nice whole tens value, we're just going to add 4 to it to make it 30. Okay, so right here, we took our 26 and we added 4 to it to make it 30, but we also have to add 4 to our minuend, which makes it 78. 78 minus 30 is an easy calculation, and that's going to give us 48. And then if you have a lot of zeros to work with, it's easier to just subtract 74 minus 6, and that gave us 68, and then just add the zeros back to our computation. So several techniques for mental computation. There are homework questions involving mental computation. Please try to do it mentally. I mean, you could pull out a calculator and get it done, but that's not doing yourself any good. It's not going to do your students any good. Really, really try to do the mental computation stuff in your head to make sure you have techniques that you can share with your students. If you have any questions about this or anything else, please let me know, and I hope you have a wonderful day.